Hello and welcome to the introductory lesson of the Big Data and Hadoop Developer course offered by Simplilearn. In this lesson, you'll get an overview of the course. Just like the cloud, big data is a baffling tech term to most people. Although it could be the next big thing, a buzzword of sorts, not many can give a definitive answer to what it is. If you happen to mention big data, you could be well subjected to questions such as, is it a tool, a product, and is big data only for big businesses? And many more in the same vein. But what is big data? It's just the huge amounts of data, both structured and unstructured, a business has to deal with on a daily basis. Now that being said, why is it important to a business, or for that matter, you? To use this phenomenal amount of data to its advantage, a business must fully grasp the possibilities of analyzing big data, and thereby making informed decisions to stay ahead of the curve. There has to be a reason why many analysts are calling big data a new competitive advantage, right? Let's look at Gartner's 3 V's model to define big data. According to the American IT research and advisory firm Gartner Incorporated, big data is high-volume, high-velocity, and/or high-variety information assets that demand cost-effective, innovative forms of information processing that enable enhanced insight, decision-making, and process automation. Today, the size, volume, complexity, variety, and the rate of growth, velocity of the data that organizations handle have reached such unbelievable levels that traditional processing and analytical tools fail quite miserably. Are you still wondering if you can come up with a rigorous definition of big data? Yes? Then know that you are not alone. Though people may be divided on how best to define big data, few are likely to dispute that these large pools of data are integral to improved future projects. But what is certain is that understanding and utilizing big data is a seriously daunting task. The sheer volume of data that's captured and analyzed will pave the way for a better economic environment only if it's effectively used to discern patterns that enable better decision-making. Big data is not just a buzzword or a fad. It's something that will undoubtedly touch businesses and people's lives the world over. For people who think that this is just another term that only the tech industry seems to care about, here are a few facts about big data that will likely convince them that big data is a revolution in the making. Read on, skeptics. The data volumes are exploding. More data has been created in the past 2 years than in the entire previous history of the human race. If you burned all the data created in just one day onto DVDs, you could stack them on top of each other and reach the moon twice. Every minute we send 204 million emails, generate 18 million Facebook likes, and send 278,000 tweets. Google alone processes, on average, over 40,000 search queries per second, making it over 3.5 billion in a day. Around 100 hours of video are uploaded on YouTube every minute, and it would take you around 15 years to watch every video uploaded by users in just one day. Today's data centers occupy an area of land equal in size to almost 6,000 football fields. By better integrating big data analytics into healthcare, the industry could save $300 billion a year. That's equal to reducing the healthcare costs of every man, woman, and child by $1,000 a year. The image here gives a very real picture of the evolution of big data. Here, the data size and complexity have been mapped against computing timeline. In the early 1970s, in fact even before that, the focus was on generation and storage of data. Mainframes were used for basic data storage. During the 1980s and 90s, the focus was on data utilization, for which relational databases and other data-intensive applications were brought into the picture. In the 2000s, the spotlight was on data-driven technology, for which structured data, unstructured data, and multimedia were used. Throughout this evolution phase, we saw an exponential growth in data volume. Consider the following case study. In 2011, Netflix made one of the biggest decisions it'll ever possibly make. It wasn't anything material, but rather it was about content. The U.S. headquartered company outbid major cable networks like AMC and HBO to win the rights for a U.S. version of House of Cards, getting them 2 seasons with 13 episodes each. With a cost of $4 to $6 million per episode, this 2-season price tag was over $100 million. Netflix had never before taken such a big gamble on the content side. So why did Netflix make such a big bet? And how did big data analytics factor into the decision? Let's find out. Now, before making the $1 million investment, Netflix knew a lot of users watched the David Fincher-directed movie, The Social Network, from beginning to end. The British version of House of Cards had been well watched. Those who watched the British version, House of Cards, also watched Kevin Spacey films and/or films directed by David Fincher. With the help of big data analytics, Netflix drew conclusions from these 3 synergistic factors before greenlighting the popular show. Combining these factors, obviously the popularity of political thrillers, makes it seem like an easy decision for Netflix to make. Licensing movies from studios is expensive, so Netflix uses data which is generated from its 69.17 million worldwide streaming customers to help pick the movies from the limited ones to license that the viewers will most enjoy. Do you have data and use it to help you make decisions? If not, Netflix provides a good case for why you should. So what are the predictions for big data in the near future? Market size. According to the International Data Corporation, IDC, the big data and analytics market will reach $125 billion worldwide in 2015, with growth at 6 times faster than IT. Skill gap. According to the McKinsey Global Institute, by 2018, the United States alone could face a shortage of 140,000 to 190,000 people with big data developer skills, as well as 1.5 million managers and analysts with the know-how to use the analysis of big data to make effective decisions. Buying and selling data will soon become the new bread and butter for business across the globe. Big data and Hadoop certification training from Simplilearn is designed to ensure that you are job-ready to take up an assignment in big data. This training not only equips you with essential Hadoop skills, but also gives you the required work experience in big data analytics via implementation of real-life industry projects that span 3 months. After completing this course, you'll be able to master the concepts of the Hadoop framework and its deployment in a cluster environment, learn to write complex MapReduce programs, perform data analytics using Pig and Hive, acquire in-depth understanding of the Hadoop ecosystem including Flume and Apache Oozie workflow scheduler, master advanced concepts of Hadoop 2.7 including HBase, Zookeeper, and Scoop, get hands-on experience in setting up different configurations of the Hadoop cluster, work on real-life industry-based projects using Hadoop. The course flow is as follows. First, internalize the domains, which includes Introduction to Big Data and Hadoop, Concepts and Architecture of Big Data Tools, Installation and Configuration of Hadoop Components, such as MapReduce, Yarn, HDFS, Pig, Hive, HBase, Zookeeper, Scoop, and Flume, and Hadoop administration, troubleshooting, and security. The next step is to master the components, which includes Hadoop 2.7, Yarn, MapReduce, HDFS, Pig, Hive, HBase, Zookeeper, Scoop, and Flume. Next, you'll learn to manage the following: structured, unstructured, and semi-structured data, Hadoop ecosystem and complex business problems, deployment of Hadoop cluster, and writing complex MapReduce programs. You'll then work on projects. The different projects in this course include optimizing data storage using HDFS in cloud environment, using MapReduce to sort and filter data, using Pig and Hive as replacement of Java, using HBase to process data in real time, using Flume and Scoop to process unstructured data, and so on. Once these steps are covered, you are all ready to take the last step, which is to get certified. This course will facilitate you to achieve Big Data Hadoop Development Certification with Hadoop 2.7 after successfully completing a full-scale industry project and an objective test of 45 questions. This concludes the course introduction. The next lesson is Introduction to Big Data and Hadoop. Wishing you all the best for this course. Happy learning! Hi everyone, and welcome to Big Data Hadoop Developer course offered by Simplilearn. Now in this lesson, we'll be doing the Introduction to Big Data and Hadoop, and we'll provide an introduction to big data. Furthermore, it'll introduce Hadoop as a big data technology. After completing this lesson, you will be able to explain data explosion and the need for big data, explain the concept of big data, describe the basics of Hadoop, and describe the history and milestones of Hadoop. Explain how to use Oracle VirtualBox to open a VM. Over the last decade, there's been an incredible explosion of data in just about every sector. It's estimated that over 2.5 exabyte or 2.5 billion gigabytes of data is generated daily from various sources. That's a lot of data. Now, here are some of the sources of this big data explosion. A large stock exchange, such as the New York Stock Exchange, generates more than 1 terabyte of data daily. Worldwide, there are approximately 5 billion mobile phones in use. Of these, nearly 1.75 billion are estimated to be smartphones. YouTube users upload more than 48 hours of video every minute. Every second of HD video generates bytes 2,000 times more than that required to store a single page of text. Large social networks like Twitter and Facebook generate more than 10 terabytes of data daily. There are more than 30 million networked sensors in the world, and each of them transmits data continuously. There are 3 primary types of data. The first is structured data, which can be represented in a tabular format and stored in relational databases like MySQL, Oracle Database, and DB2. The second one is semi-structured data, which doesn't have a formal data model, though it may have some semblance of a structure. For example, XML files represent semi-structured data. Now the third is unstructured data, which doesn't have a predefined data model. Text files, weblogs, and machine logs are good examples of unstructured data. Did you know that according to an estimation, approximately 90% of the world's data has been created in the last 2 years? It includes 10% of structured data and 80% of unstructured data that are difficult to analyze. The structured formats, such as databases, have limitations while handling large data sets, and there's difficulty in integrating distributed information. Furthermore, most business users aren't aware of the requirements during IT system development. Potentially valuable data for varied systems like enterprise resource planning or ERP and supply chain management or SCM are either dormant or discarded, forming a data puddle within enterprises. It's often too expensive to justify the integration of large volumes of unstructured data. Therefore, big data is needed to analyze and integrate the enterprise's large data sets, irrespective of the data types. Big data is a broad term for large or complex data sets that are difficult to be sorted using on-hand data management tools or traditional data processing applications. Various sources of big data are weblogs, social media, sensor networks, internet text, pages and documents, search index data, atmospheric science, astronomy, biochemical, medical records, scientific research, military surveillance, and photography archives. Here are the characteristics of big data. Variety encompasses managing the complexity of data in different structures ranging from relational data to logs and raw text. Velocity accounts for managing the streaming of data and the movement of voluminous data at a high speed. Volume denotes managing the huge scaling of data ranging from terabytes to zettabytes. Voluminous data is useless without accuracy, as incorrect data causes concern in organizations. Veracity manages accuracy of data and its analyses, especially in automated decision-making process. Data veracity is essential if the organization aims to be information-centric. And here are more characteristics of big data. Big data is variable, which means the meaning of the data is constantly changing. This makes it relevant in sentiment analyses. To perform a proper sentiment analysis, Algorithms need to understand the context and decipher the exact meaning of a word in that context. Visualization makes voluminous data comprehensible. With correct analyses and visualizations, raw data can be used. Visualizations mean complex graphs that can include variables of data while still remaining understandable and readable. The value of data is in analyses, which turns data into information, followed by knowledge. Based on data value, organizations can become information-centric. Big data technology helps to respond to the big data characteristics. Now, here are the 3 characteristics of big data technology. Firstly, it helps to cost-effectively process the growing volumes of data. For example, per IBM, big data technology has helped to turn the 12 terabytes of tweets created daily into improved product sentiment analysis. It has converted 350 billion annual meter readings to predict power consumption better. The second characteristic of big data technology is that it helps to respond to the increasing velocity of data. For example, it's scrutinized 5 million trade events created daily to identify potential frauds. It's helped to analyze 500 million daily call detail records in real time to predict customer churn faster. The third characteristic of big data technology is that it helps to collectively analyze the widening variety of data and handles failure of isolated nodes and tasks assigned to such nodes. It can also turn data into actionable insights. For example, it's helped to monitor hundreds of live video feeds from surveillance cameras to target points of interest for security agencies. It has also been able to exploit the 80% data growth in images, videos, and documents to improve customer satisfaction. According to Gartner, big data is a high-volume, high-velocity, and high-variety information asset that demands cost-effective, innovative forms of information processing for enhanced insight and decision-making. Big data technology enables IT to leverage multiple sources of data. Now, the major sources of data include application data, which has high volume and throughput, and it's structured. Machine data, which has high velocity, is semi-structured and needs to be ingested at a high speed. Social data, which has high variety, is unstructured and requires you to establish the veracity of the data. Enterprise data, which has variety, is available in different formats like PDFs, spreadsheets, and documents. It's highly unstructured and can be voluminous. Here are the requirements of the traditional IT analytics approach and its challenging factors. The traditional IT analytics approach requires the business team to define questions before IT development. Furthermore, the team needs to predefine the data sources and structures. The business team's usually challenged if it has iterative and volatile requirements or if data sources keep changing. Let's now look at the process involved in traditional IT analytics approach. In a scenario of traditional IT systems development, the requirements are defined first. This is then followed by the solution design and build. Once the solution is implemented, queries are executed. If there are new requirements or queries, the system is redesigned and rebuilt. Here are the requirements and the challenging factors that have to be overcome for using big data technology as a platform for discovery and exploration. The big data technology approach requires the business team to define data sources and establish a hypothesis. Big data technology should enable explorative analysis. The IT team should integrate data systems and sources as required based on new business questions and the hypotheses. Let's now look at the process involved in big data technology approach. At the outset, the initial data sources are identified. The IT team creates a platform for creative exploration of available data and content. The business team then determines the questions to ask and tests their hypotheses. Any new question leads to the addition and integration of data sources without the need to redesign and rebuild the platform. Big data technology helps to understand and navigate big data sources, manage and store a huge volume of various data, process data in a reasonable time, ingest data at a high speed, analyze unstructured data, and bear faults and exceptions. Okay, now big data technology appeals to various sectors and it's used for a variety of use cases. Per Cloudera, the technology has found uses in industries such as automotive, communications, consumer packaged goods, financial services, education and research, high technology and industrial manufacturing, life sciences, media and entertainment, online services and social media, healthcare, oil and gas, retail, travel and transportation, utilities, and law enforcement and defense. Now, there are two key challenges to be addressed by big data technology. These are handling the system uptime and downtime, and combining data accumulated from all systems. To overcome the first challenge, big data technology uses commodity hardware for data storage and analysis. Plus, it helps to maintain a copy of the same data across clusters. To overcome the second challenge, big data technology analyzes data across different machines and then merges that data. Hadoop helps to leverage the opportunities provided by big data and overcome the challenges it poses. Let's now look at the definition of Hadoop and its requirement. Hadoop is an open-source Java-based programming framework that supports the processing of large data sets in a distributed computing environment. It's based on Google File System or GFS. The next question to be addressed is why Hadoop is used. Hadoop runs a number of applications on distributed systems with thousands of nodes involving petabytes of data. It has a distributed file system called the Hadoop Distributed File System or HDFS, which enables fast data transfer among the nodes. Furthermore, it leverages a distributed computation framework called MapReduce. Hadoop originated from the Nutch open source project on search engines and works over distributed network nodes. In 2003 and 2004, Google released two papers that provided insight into their success: the Google File System or GFS and MapReduce simplified data processing on large clusters. The papers told the world how Google performed large-scale data processing. In July 2005, Nutch used GFS to perform MapReduce operations. In February 2006, Nutch started a Lucene subproject which led to the era of Hadoop. In April 2007, Yahoo started using Hadoop on a 1,000-node cluster. In January 2008, Apache took over Hadoop and made it a top-level project. In July 2008, a 4,000-node cluster with Hadoop was tested by Apache. The performance of that cluster was surprisingly the fastest when compared to the other technologies implemented that year. In May 2009, a test revealed that Hadoop successfully sorted a petabyte of data in 17 hours. Hadoop reached version 1.0 in December 2011. It is open source and written in Java. On May 23, 2012, Hadoop 2.0.0 was released, which delivers significant features, including Yarn, high availability for HDFS, HDFS Federation, HDFS snapshots, NFSv3 access to data in HDFS, support for running Hadoop on Microsoft Windows, binary compatibility for MapReduce applications built on Hadoop 1.x, and substantial integration testing with the rest of the projects in the ecosystem. The current version of Hadoop is 2.7.1. It was released on the 6th of July 2015. It is completely open source and written in Java. Yahoo was the first company to design and use Hadoop as a core part of their system operations. Now Hadoop is a core part of systems at internet companies such as Facebook, LinkedIn, Twitter, and many enterprise organizations such as JP Morgan and Chevron. VMware Player is a free software package offered by VMware Incorporated used to create and manage virtual machines. The VMware Player can be downloaded for personal use from the URL mentioned here. The image here shows you where to access CloudLab from. Click Lab Access to get the screen similar to the image here. The basic hardware requirements for working on VMware Player are as follows: 1 GHz processor to support Intel VT or virtualization technology, 1 GB of RAM, and 150 MB hard disk to install the application. However, it is recommended that you have a 2 GHz processor and 4 GB of RAM for optimum performance. The Oracle VirtualBox is used to open virtual machines. Apple Macintosh users use the free VM player, as the VMware Fusion player is available only for trial or limited usage. Download the latest version of VirtualBox compatible with your machine and firewall settings from the URL mentioned here. Now let's summarize the topics we talked about in this lesson. Big data is a term applied to data sets that cannot be captured, managed, and processed within a tolerable elapsed and specified time frame by commonly used software tools. Big data relies on volume, velocity, and variety with respect to processing. Data can be divided into three types: unstructured, semi-unstructured, and structured data. Big data technology understands and navigates big data sources, analyzes unstructured data, and ingests data at a high speed. Hadoop is a free Java-based programming framework that supports the processing of large data sets in a distributed computing environment. This concludes Introduction to Big Data and Hadoop. In the next lesson, we're going to focus on Hadoop architecture. Hey everyone, and welcome to Big Data and Hadoop Developer course offered by Simplilearn. This lesson, Hadoop architecture, will provide detailed information regarding the Hadoop architecture. After completing this lesson, you'll be able to describe the use of Hadoop in commodity hardware, explain the various configurations and services of Hadoop, differentiate between a regular and a Hadoop distributed file system, explain HDFS architecture. An understanding of the key terms is essential when discussing Hadoop architecture. The term commodity hardware refers to regular PCs which can successfully be used to make a cluster. The word cluster refers to multiple systems logically interconnected in the same network for a distributed mode process. Nodes are the commodity servers which are interconnected through a network device. Hadoop is a framework which is often used in commodity hardware. It supports the concept of distributed architecture. The diagram you see here represents the cluster of nodes connected and installed with Hadoop. The maximum number of nodes that can reside in a single rack is approximately 30 to 40. However, it's not an exact count. You can have more nodes if you have adequate network speed. Normally, the uplink from rack to node is 3 to 4 gigabits per second, and the uplink from rack to rack internally is 1 gigabit per second. Hadoop supports three configuration modes when implemented on commodity hardware: standalone, pseudo-distributed, and fully distributed mode. Click each tab to know more. Now, in a standalone mode, all Hadoop services run in a single Java virtual machine or JVM on a single machine. In a pseudo-distributed mode, each Hadoop service runs in its own JVM but on a single machine. And finally, in a fully distributed mode, the Hadoop services run in individual JVMs, but these JVMs reside on different commodity hardware in a single cluster. The core Hadoop services are Name Node, Data Node, Resource Manager, Application Master, Node Manager, and Secondary Name Node. Generally, in the fully distributed mode, the Name Node, Secondary Name Node, and Application Master are identified as master services, while the Data Node and Node Manager are classified as slave services. There are two major components of Apache Hadoop: Hadoop Distributed File System, or HDFS, and Hadoop MapReduce. HDFS is used to manage the storage aspects of big data, and MapReduce is responsible for processing jobs in a distributed environment. Prior to 2011, storing and retrieving petabytes or zettabytes of data had three major issues: cost, speed, and reliability. A traditional file system approximately costs $10,000 to $14,000 per terabyte. Searching and analyzing data was both time-consuming and expensive. And if search components were saved in different servers, fetching data was a probability. Things would break every day in different ways. Here, HDFS, or Hadoop Distributed File System, comes into the picture. Its major USPs are: 1. It is designed to run on regular commodity hardware that costs around $4,000 per terabyte. Since it is an open-source software, it can be used with zero licensing and support costs. This cost advantage lets organizations store and process more data per dollar than traditional systems. In big data deployments, the storage cost often determines viability of the system. 2, it can easily deliver more than 2 gigabits of data per second per computer to map reduce. This means large Hadoop clusters can read or write more than a terabyte of data per second. 3, it copies data multiple times and distributes the copies to individual nodes, placing at least one copy on a different server. As a result, the data on nodes that crash can be found within the cluster, which allows processing to continue while the failure is resolved. HDFS is a distributed file system that provides great access to data across Hadoop clusters. Like other Hadoop-related technologies, HDFS is a key tool for managing pools of big data and supporting big data analytics applications. A college library was gifted a massive collection of books by a patron. The books were very popular titles. The librarian decided to arrange the books in a small rack and distribute multiple copies of each book in other racks so that students can find the books easily. Similarly, HDFS creates multiple copies of a data block and keeps them in separate systems for easy access. The table you see here compares a regular file system with HDFS. In a regular file system, each block of data is small, usually about 51 bytes. However, in HDFS, each block is of 64 megabyte by default. A regular file system provides access to large data, but this feature of the file system may suffer from disk I/O problems, mainly due to multiple seek operations. HDFS can read large quantities of data sequentially after a single seek. This makes it unique since all of these operations are performed in distributed mode. The basic characteristics of HDFS that make it popular are: first, HDFS has a high fault tolerance. An HDFS instance may consist of thousands of server machines, each storing a part of the file system's data. There exists numerous components, and each has a probability of failure and non-functionality. The core architectural goals of HDFS are detection of faults and quick automatic recovery. Second, HDFS provides high throughput. HDFS is designed to store and scan millions of rows of data and to count or add some subsets of data. The time required in this process is dependent on the involved complexities. Third, HDFS is suitable for applications with large data sets. Traditionally, HDFS has been designed to support high throughput of data sets in batch-style jobs. Fourth, HDFS is suitable for applications with streaming access to file system data. They're not targeted for general-purpose applications. HDFS is designed more for batch processing rather than for interactive use. The emphasis is on high throughput of data access rather than low latency of data access. Finally, HDFS is designed in such a way that it can be built on commodity hardware and heterogeneous platforms. The key features of HDFS are as follows. It creates multiple replicas of each data block and distributes them on computers throughout a cluster to enable reliable and rapid data access. It's the storage system for both input and output of MapReduce jobs. This file system can be accessed by using the HDFS protocol to perform input-output operation on the file which is stored in HDFS. Block storage metadata controls the physical location of a block and its replication within the cluster. Each block is replicated to a few physically separate machines. However, the count can be modified by the administrator. As we discussed earlier, HDFS architecture consists of name node and secondary name node services, which constitute the master services. The data node service falls under the slave service. The master service is responsible for accepting a job from clients. It has the task of ensuring that the data required for the operation is loaded and segregated into chunks of data blocks. HDFS exposes a file system namespace and allows user data to be stored in files. A file is split into one or more blocks, stored and replicated in data nodes. The data blocks are then distributed to the data node systems within the cluster. This ensures that replicas of the data are maintained. Prior to Hadoop 2.0.0, the name node was a single point of failure, or SPOF, in an HDFS cluster. Each cluster had a single name node, and if that machine or process became unavailable, The cluster as a whole would be unavailable until the name node was either restarted or brought up on a separate machine. This impacted the total availability of the HDFS cluster in two major ways. In the case of an unplanned event such as a machine crash, the cluster would be unavailable until an operator restarted the name node. Planned maintenance events, such as software or hardware upgrades on the name node machine, would result in windows of cluster downtime. The HDFS High Availability, or HA feature, addresses these problems by providing the option of running two redundant name nodes in the same cluster in an active-passive configuration with a hot standby. Now, this allows a fast failover to a new name node in the case that a machine crashes or a graceful administrator initiated failover for the purpose of planned maintenance. In a typical HA cluster, two separate machines are configured as name nodes, and at any instance, one of the name nodes is in an active state and the other is in a standby state. The active name node is responsible for all client operations in the cluster, while the standby is simply acting as a slave, maintaining enough state to provide a fast failover if necessary. Hadoop supports two major implementations: one, quorum-based storage, and two, shared storage using NFS. Quorum-based storage refers to the HA implementation that uses Quorum Journal Manager, or QJM. For the standby node to keep its state synchronized with the active node in this implementation, both nodes communicate with a group of separate daemons called journal nodes. When any namespace modification is performed by the active node, it durably logs a record of the modification to a majority of these journal nodes. The standby node is capable of reading the edits from the journal nodes and is constantly watching them for changes to the edit log. As the standby node sees the edits, it applies them to its own namespace. In the event of a failover, the standby will ensure that it has read all the edits from the journal nodes before promoting itself to the active state. Now, this ensures that the namespace state is fully synchronized before a failover occurs. In shared storage using NFS for the standby node to keep its state synchronized with the active node, this implementation requires both the nodes to have access to a directory on a shared storage device, for example, an NFS mount from an NAS. HDFS components include different servers such as name node, data node, and secondary name node server. The name node server is the core component of an HDFS cluster. There can be just one name node server in an entire cluster. It's responsible for maintaining the file system namespace. The name node helps to execute file system namespace operations like opening, closing, and renaming of files and directories which are present in HDFS. Information of the data and the metadata is stored in the namespace image and the edit log. It also determines the linking of blocks to data nodes. Furthermore, the name node is aware of the data node status. That is, it knows the data node in which certain data is stored. It's also a critical single point of failure. If it fails, the entire cluster goes down. However, the name node server can be partially restored by using a secondary name node server. The data node is a multiple instance server. There can be n number of data node servers depending on the type of networking and storage system. The data node servers are responsible for storing and maintaining the data blocks which are provisioned by the name node server on the basis of the type of job submitted by the client. It's also responsible for storing and retrieving the blocks when referred by clients or the name node. Furthermore, the data node servers read, write requests, and perform block creation, deletion, and replication upon instruction from the name node. There can be only one secondary name node server in a cluster. It's responsible for maintaining a backup of the name node server. However, you cannot treat the secondary name node server as a disaster recovery server. It will partially restore the name node server in case of failure. The secondary name node server maintains the edit log and namespace image information which is synced with the name node server. Now, at times, the namespace images from the name node server are not updated. So, you cannot totally rely on the secondary name node server for the recovery process. HDFS exposes a file system namespace and allows user data to be stored in files. HDFS has a hierarchical file system with directories and files. The name node manages the file system namespace, allowing clients to work with files and directory subtrees. A file system supports operations like create, remove, move, and rename. The name node, apart from maintaining the file system namespace, records any changes to metadata information. The name node maintains two persistent files, a transaction log called an edit log and a namespace image called an FS image. The edit log records every change that occurs in the file system metadata, such as creating a new file. The edit log is stored in the name node's local file system. The entire file system namespace, including mapping of blocks, files, and file system properties, is stored in FS image. This is also stored in the name node's local file system. However, metadata loads into its memory the blocks of data that reside on a specific data nodes at startup when the new data nodes join a cluster. Metadata then periodically loads at user-defined or default intervals. When the name node starts up, it retrieves the edit log and FS image from its local file system. It then updates the FS image with edit log information and stores a copy of the FS image on the file system as a checkpoint. The metadata size is limited to the RAM available on the name node. A large number of small files would require more metadata than a small number of large files. Hence, the in-memory metadata management issue explains why HDFS favors a small number of large files. If a name node runs out of RAM, it'll crash, and applications won't be able to use HDFS until the name node is online again. Each file is split into one or more blocks stored and replicated in data nodes. Data nodes manage names and locations of file blocks. Each file block is 64 megabytes by default. Now, for large files, it's better to increase the block size to 128 megabytes. Doing this decreases pressure on the name node's memory, but this potentially reduces the amount of parallelism that can be achieved as the number of blocks per file decreases. Each map task operates on one block, so if tasks are lesser than nodes in the cluster, the jobs will run slowly. However, this becomes a lesser issue when the average MapReduce job involves more files or larger individual files. Some benefits of the data block approach include simplified replication, fault tolerance, and reliability, and shielding users from storage subsystem details. In HDFS, unstructured data is represented in the form of data blocks. If there's a default size for the data blocks, it can be reset by the user or the administrator. Block replication refers to the creation of replicas of a block in multiple data nodes. Usually, the data is split in the form of parts, such as Part 0 and Part 1. HDFS performs block replication on multiple data nodes, so that if any error exists on one data node server, the job tracker service, which is present in the name node server, will resubmit the job to another data node server. Each file is split into a sequence of blocks, except the last one. All blocks in the file are of the same size. Now, blocks are replicated for fault tolerance. The block replication factor is usually configured at the cluster level, but it can also be configured at the file level. The name node receives a heartbeat and a block report from each data node in the cluster. A block report contains all of the blocks on a data node. An application can also specify the number of replicas of the file needed, such as the replication factor of the file. This information is stored in the name node. One of the suggested replication topologies could be having the first replica placed on the same node as the client. The second replica is placed on a rack different from the first rack. The third replica is placed on the same rack as the second but on a different node. On the chart shown here, you can see a Hadoop cluster with 3 racks represented by dark blue pillars. Each rack contains multiple nodes represented by rectangular boxes. For example, you'll see a box labeled R1N1, which represents node 1 on rack 1. To make it simple, each rack shown here has 8 nodes. At the top, you'll see the name node shown in yellow. Follow the path of a single data block, block B1, shown in purple on this chart. B1 is first written to node 4 on rack 1. A copy is then written on a different rack, rack 2. More specifically, it's written to node 5 on rack 2. The third and final copy of the block is written to the same rack as the second copy, rack 2, but to a different node, node 1. HDFS provides various access mechanisms. A Java API can be used for applications. There's also a Python and C language wrapper for non-Java applications. A web GUI can also be utilized through an HTTP browser. An FS shell is available for executing commands on HDFS. Olivia Tyler is the EVP of IT Operations with Nutro Worldwide Incorporated, and she's decided to use HDFS for storing big data. She'll use HDFS shell to store the data in a Hadoop file system, and she'll execute various commands on it. Okay, time to summarize the topics we covered in this lesson. Hadoop works on 3 configurations: standalone, pseudo-distributed, and fully distributed mode. The 2 core components of Apache Hadoop are HDFS and MapReduce. The HDFS layer contains name node, secondary name node, and data node. HDFS can be used to handle big data sets with its inherent features of fault tolerance, high throughput, and streaming data access.
Hey, want to become an expert in big data? Then subscribe to the Simplilearn channel and click here to watch more such videos. To nerd up and get certified in big data, click here.